Hi, everyone. Thanks for joining us today. I'll just give a quick overview of how we're going to do this, and then I'll do some introductions. My name is Colette Drewars, and I'm a journalist at the Canadian Press. We're here today for the Romanowski Lecture, and for those of you who don't know about the Romanowski Lecture, it's based on an award that goes out every year for scientific work that relates to environmental problems. And as you know, based on who our guest lecturer is today, that was awarded to John Pomeroy. It was established in 1994, and it's based on internationally renowned meteorologist Miroslav Romanowski. So I'll post a little bit more details about him in the chat box if anyone wants to get a few more details about that. And then I'll start with introductions before we head into John's lecture. With us today is John Pomeroy, who's the Canada Research Chair in Water Resources and Climate Change. His research focuses on cold regions, hydrology, its processes, measurements, and prediction. He leads the Global Water Futures, which is the largest university-led freshwater research in the world. And Caroline Aubrey-Wake is a PhD candidate at the University of Saskatchewan. She is based in Canmore, Alberta, lucky her, as well as John. And she, under John's supervision, is trying to understand how melting glaciers and a changing landscape impact water resources. And I've already introduced myself. I got to know John when I was the environment reporter at the Calgary Herald during the 2015 floods, and still do some work at the Canadian Press as well on the environment and climate change, as well as many, many other news events, particularly COVID in these times. So I'll leave it at that and turn it over to John.
Well, thank you so much, Colette, and it's a great honor and pleasure to be speaking this morning and giving a lecture that memorializes the advances that Miroslav Romanowski made. I will set up some screen sharing here, and then go into a what will be hopefully relatively short discussion of the talk, which is on freshwater futures for Canada. And I will try to bring together some of the research that I've been doing and some of the global water futures research, largely dealing with the issues of climate change, climate warming, and the changing cold regions hydrology of Canada, and what this means for our water futures. The first, stepping back a bit, water is the basis of our life. Water is life, and our human activity that is governed by water also regulates the global climate. So both the water system has a feedback role to the global climate through water vapor in the atmosphere, the clouds, and the global water cycle. And then humans manage water. We have for much of our developed history, and that managed water cycle also influences the global climate, and water permits our industrial activities, which have resulted in excessive greenhouse gas emissions for centuries now, which have strongly changed the global climate. Of course, water supporting in Canada. Canada is one of the most water dependent and water countries in the world, because it's been the basis of our development as a nation, the basis for our indigenous nations that have been here for millennia, and sustains our ecosystems, sustains our food production, our economy, and even the locations of most of our cities is based upon perhaps canoe routes and even going back to the fur trade. However, things are changing, and Canada is warming due to climate change, and warming twice as fast as the rest of the world. If you look at temperature changes from the record, and this is just the moving average, the black line, it's a little bit easier to see. From the 1940s to the current time, you'll see a tremendous increase in temperature to 2016. That is carried on to recent years, and 2020 is looking to be an exceptionally warm year globally. In Canada, measured climate change is occurring across the country, but it's fastest in the north and in the western part of the country. And if you go to the parts of Western Canada, the settled south, the prairie belts, we're seeing already 1 to 2 degrees of warming. And if we go up into the north, into the Northwest Territories, Yukon and Nunavut, we're seeing already 3 degrees of warming. Up around the Nunavut in the Northwest Territories, they've measured 6 degrees of warming for winter minimum temperatures since 1960. 6 degrees already. So remember that the UN conventions on climate change are concerned about keeping global warming averages to 1.5 degrees over the whole Earth. But in Canada, we've well exceeded that, and particularly in the north. So we are the canary in the coal mine, and a place the rest of the world can look to see what climate change looks like. And not just Canada, Russia is also in the same boat of being in the northern circumpolar world. When we look to the future, we see even more warming and of course further impacts of this. And so these are two representations of future average temperatures over Canada. The upper layer graphs is a representation called representative concentration pathway 4.5, which the models presume greenhouse gas stabilization by 2100. And even in that case, we're still seeing a further warming of anywhere from 1.5 to 4 degrees over parts of the country. Yeah, however, that's not the path we're on. We're not on the path to stabilize greenhouse gas emissions. We're on the path of RCP 8.5, which is ineffective greenhouse gas controls and numerous treaties which are not implemented in a meaningful way by the main emitting countries. And the path we're on will lead to warming 4 to 9 degrees over Canada, and maybe some 10 to 11 degrees in the far north by the end of the 21st century, which is hard to imagine what that degree of warming would make our country look like. But certainly the impacts that we've seen already with the massive increase in forest fires, as you see below at Fort Mac, or the diversion of waters to lakes. This is a lake bed at Kluane Lake and a dust storm in that area in Yukon. And that's where the Adabaska Glacier has retreated so much that it no longer feeds water into Kluane Lake by the Slims River, and the lake levels have dropped 1.6 meters. And that just happened a few years ago. So we're in the midst of this already and looking at pretty scary things in the future. And then there's precipitation, because remember, the water cycle is an intrinsic part of the world's climate system. And with warmer atmosphere, we have a greater capacity to hold water vapor in the atmosphere and greater energy in there for severe storms and movement of storms, and then also changes in the dynamics of precipitation already occurring and projected to occur over time. So again, if we look at climate models, this is Canadian climate data and scenarios under greenhouse gas stabilization, by the late part of the century, we'd be seeing increases in precipitation of sort of 10 to 20% over northern Canada and less than 10% over southern Canada. But for the path we're on, we would see increases of 10 to 20% over southern Canada and increases towards 40% in northern Canada. But these are average increases in precipitation, and the worrisome thing is the increase in severe storms is already recorded and lines up very much with temperature rises across the country. In the prairie provinces, the increase in multiple day storms has increased dramatically. Examples being the Calgary Flood of 2013, or the floods on the eastern prairies in 2014. In eastern Canada, you can think of the floods in the Ottawa River, where persistent storms parked over the Ottawa River basin in springtime when there was a record snowpack. And then you get flooding events, exceptional ones, such as in Calgary or in the prairies or in eastern Canada. And every part of the country is seeing this now, including this year in northern Canada. And so we are having problems already. So Canada has elements of an emerging water crisis that crisis has a number of elements to it. Despite the fact that we have exceptional water availability in Canada, most Canadians live in the south, whilst most of the rivers flow north. So that water availability is not where the population is, and that's just how we've developed. But that means we have parts of the country which do have regional water stress, such as parts of southwestern Ontario, the Canadian prairies, the Okanagan, and other interior basins in British Columbia. And more of the country is expected to experience that stress on a regular basis in the future. As I mentioned, our economy has developed to become exceptionally reliant upon water availability for all aspects to it. And we also, associated with the climate change and the rapid warming that we're undergoing, we're seeing a dramatic increase in events such as floods, droughts, and wildfires. And so just in this century alone, we're only 20 years into it. We've already seen the worst droughts in our recorded history. We've already seen the worst floods in our recorded history. We had roughly $1 billion of payouts for natural disasters associated with water from the year of Confederation to the year 2000. And it's been running at over $1 billion a year since the year 2000. We're into the 30 billions now for natural disasters. So it was up to 28 billion by 2017. So it's expensive, and it causes tremendous social disruption, economic disruption, and environmental disruption to have these extreme events occurring on such a regular basis now. There are particular water security and climate challenges associated with mountain regions around the world. Rising temperatures at high elevations are associated with drought for streams and rivers that feed from mountains. The melt of snow, the retreat of glaciers, the lack of water availability, the forest fires we saw in California and the Pacific Northwestern US this summer are examples of that. The British Columbia fires from 2 and 3 years ago, further examples. The retreat of glaciers like Pedro Glacier, which has retreated kilometers since the 1950s. And this photograph is 2014. It's out of date, as Caroline may show you later. And the loss of snow cover, we were worried about the survival of ski resorts a few years ago in the Western Mountains because of early snow melt. And some were closing in February in some of the snow drought years. And then there's flooding associated with this as well. As the systems shift from snow-driven systems to rainfall-driven systems, rainfall is flashier, precipitation is delivered faster than snow can melt, and so it makes the vulnerability of downstream communities to flooding much higher. And as Calgary and interior BC communities, it can certainly attest to. I mentioned glaciers. This is an artist's rendition of Plato Glacier. It's the longest studied glacier in the world. It's the one I just showed you retreating several kilometers. There's its path of retreat. If you'd been out here in the 1970s, the ice would have been down well past here, and now it's retreated further away, leaving a system of lakes. But Plato Glacier is emblematic of the loss of our mountain snowpacks, and we've been studying it intensely for years. These are observations and model results for the ice elevation in Plato Glacier from 2010 to 2016. And you see it's lost more than 25 meters of ice moving downward over that period of time. So what you get is a crevassed, darkened surface, and then eventually lakes and bare rock exposed. The impacts on stream flow to lose such a glacier can be profound. This is taking the glacier component out of a hydrological model and look at the discharge of the creek out of Plato Glacier. This is how it was in the 60s to 70s, and this is how we predict it will be upon deglaciation without a climate change, a loss of substantial flow from late summer into early fall that would normally sustain the aquatic ecosystem of Banff National Park. I'll take you a little bit further south to another long-studied research basin, Marmot Creek, also founded in the 1960s, in this case by 1962, and one of the founders, Dr. Jim Bruce, is still around and a fellow of the Royal Society, I believe. Anyway, Marmot Creek's been a wonderful science mine for us, where we can understand the impacts of climate change on the hydrology of a forested and alpine mountain basin. And you see studies going back to the mid-1960s here, but we carry them on, and it's a wonderful place for us to look at what a typical Canadian Rockies headwater basin in the Front Ranges is behaving like, and what its future might be. And its future looks to be something that's rather different. One thing is, looking historically at Marmot Creek, so far the stream flow regime has not shifted despite substantial climate warming in that basin. But the timing and the volumes of water and the peak flows have not changed since the early 1960s. But looking forward, we can take a weather model called WRF, WRF, drive that bounded by climate simulations to produce future weather for the 21st century, and then compare the behavior of Marmot Creek under its current climate to its behavior at the end of the 21st century. And so this is just looking at the snowpack. Overall, we see an increase in temperature of almost another 4.7 degrees and a 16% increase in precipitation. That results in an overall loss of 84 millimeters of water equivalent of snowmelt over the basin. And you can look at the snow water equivalent, the snow accumulation on the ground, and how that has reduced dramatically. It's a shorter snow season and much less snowpack. And the solid lines are the average. The shaded lines are 15-year range of results. And we see some very low snow years in the future at the lower elevations. The alpine is less affected, but the tree-lined forests, which get large snowdrifts, lose those snowdrifts because of the loss of blowing snow in the future, and hence dramatically lower snow reserves in Marmot Creek to provide stream flow. And however, it's replaced to some degree by a dramatic increase in rainfall, which increases over 150% in the basin. And so under the future climate, the future stream flow of Marmot Creek is not as dire as the future snowpack is. It's coming much earlier, a 45-day advance in the spring freshet, almost a 2-month longer summer period without snow on the ground. And but the stream flow increases 16%, 18% associated with that 16% increase in precipitation. And so there's more water coming out of Marmot Creek, but it's coming earlier and over a longer period of time, and it's much more variable. If we take this up and say, can we scale these results up to a larger continental river basin? We can, but then we have to, since we're moving out of protected areas like the national parks or Kananaskis country, we have to consider water management in these models, and we have to drive these models with climate, regional climate models. And so we've done that with the research of my colleagues Simon Razavi, Alan Pietranero, and their student Fuad Yassim. And so this is a model called MESH. It's developed jointly between Global Water Futures and Environment Canada. And this is showing MESH's results, how it pieces together the whole Saskatchewan River Basin from the Rocky Mountains across the high plains in Alberta through Saskatchewan and finally into Manitoba. And so it takes supercomputers to run models of this nature. And we can put together a model like this and calculate the precipitation over the basin. There's the mountains, and there's Saskatchewan, there's Manitoba, the evaporation rates, the subsurface storage, the runoff, and you can see the mountains are generating almost all the runoff in the basin until you hit the boreal forest in the east, and then soil moisture at shallow and deeper layers. And so we can look at different years here, look at the variability, but importantly, the model gives us a robust analysis of what future stream flow might be, because those rivers supply the cities of Edmonton, Calgary, Saskatoon, Medicine Hat, through canals, Regina, and ultimately the feed into Lake Winnipeg, and where they sustain an important ecosystem, and then through the Nelson River provide water that generates hydroelectricity by Manitoba Hydro's dams, and then eventually discharges into Hudson Bay, where it makes an important contribution to the ecosystem there. And if we look at the changes in the flow volume variability over 30-year runs involving 15 RCM, so that's where we assess our uncertainty, we can look at various endpoints, the For instance, the Old Man River near the mouth, we see a steady increase in stream flow from the current time to the early mid 21st century to the late 21st century, but also an increase in variability and some very high flows in here. The Bull River near the mouth also going from about 3 billion cubic meters up to 3.5 on average, but also some very high flows. And this is reflected throughout the system. Here's the South Saskatchewan River at Saskatoon, again, a substantial increase in flows. But it's that can look like good news. Oh, a bit more water in our river, but that variability should be the first tip-off that we might have some problems. And so when we look at the flow regimes that are predicted, it's much like what we saw in Marmot Creek. There's more water, but it's coming earlier by the time we hit the 2070s, and much more variable in some cases, looking at the Battle River here, and where there are hydroelectric reservoirs, and these are considered in this simulation. In this case, the current reservoir management rules would cause the dam to have to spill on a monthly basis through the winter time, which would not be an acceptable practice. So water would have to be managed very differently under the future climates that are suggested by these simulations. There's considerable uncertainty to these. It's based upon a wide range of climate models, and precipitation is the most uncertain output of a climate model in many ways. But we bias corrected these as best we can, and taking into account irrigation and land use and reservoir operations and glacial retreat in these simulations. The glacial retreat in this case is overwhelmed by the increase in precipitation in the mountain headwaters. When we look at the Bull River at Banff, something that's a bit more mountain driven, we see we can rerun simulations for the period 2001 to 2015, which includes a severe drought, but also includes the flood, the June flood of 2013 that damaged Calgary so much. And under a future atmosphere, we can see that those peak flows are higher on the Bull River at Banff, and that is certainly a worry for those downstream users, that climate change could make the historical floods larger. And I guess the good aspect is it does not make the droughts worse from these simulations, and the low flows in this are somewhat higher, which could be good for aquatic ecosystems. So it's never a clear-cut answer with these things. You can get a bit of good and a bit of bad, but change in general is very difficult to adapt to, both the natural ecosystem and for human use. This leads lots of questions for how we might manage these futures across the country. And one thing that I and other colleagues have been encouraging the federal government to move forward with, and they have, is a Canada Water Agency. And because we have many elements of a water crisis in Canada, and we think as a group that a Canada Water Agency might provide a very valuable service, not doing everything as a federal government agency, but coordinating a national approach to creating and mobilizing knowledge that we need to predict and respond to emerging water problems and opportunities, such as predicting future floods and droughts in concert with the provinces and territories, helping predict water quality episodes that cause undrinkable water, water supply problems, helping communities make decisions about their water use, bring all water data together, surface water, groundwater, snow and ice information, water quality information. Because we have so many river basins that are changing and cross boundaries between provinces, between First Nations territories and other territories, and across the U.S. border. We need to strengthen our transboundary management to avoid disputes and anticipate them, to help adapt to climate change, to help remap our floodplains and work out strategies for reducing flood damages, and to work out how we can best manage these river basins for the good of everyone. And then what is certainly apparent to us is that Indigenous people have not been invited and involved in water management in this country through agencies like that are driven by the Canada Water Act, which doesn't mention Indigenous people. And so we need to make sure that Indigenous people are at the table for water management by co-drafting a Canada Water Act that addresses the UN rights of Indigenous people and make sure that they're at the table for water management decisions and that their viewpoints are valued and taken into account as we manage our changing water resources. And this can be done through improving collaborative river basin planning and management across the country, building partnerships for water management, restoring river basins, restoring environmental flow regimes, and conserving our soil and water better. So I think that with information, we can help make a better future for ourselves under the extraordinarily difficult century we will have with climate change. And we've learned this year alone that the only thing worse than an epidemic or a pandemic is a pandemic and a flood at the same time when communities have had to evacuate. So perhaps a better science basis to our decisions for water can help prevent future disasters and mitigate them in the same way that the Canada Health Agency is doing so under the current pandemic. So a few conclusions for us to consider, and then we'll move on with our panel discussion. But we know climate change is already having a dramatic impact on Canada's water, and it will continue in the future. The warming climate is resulting in enhanced glacial melt and retreat. Most climate models predict higher precip as well as warmer temperatures in the future, and this may lead to larger streamflow volumes for large river basins such as the Saskatchewan-Nelson, but with greater variability. And this might provide opportunities, but also will make water management more uncertain and future water developments highly uncertain as we move forward, which will create some concerns, I believe. The warming climate will also result in earlier stream flow from the mountains, and increased precip may increase floods and increase peak flows during those floods. So that's a problem for infrastructure downstream, like cities like Calgary, Edmonton, Red Deer, hydroelectricity generation, and making sure there's enough water supply for irrigation. I mean, large flows coming out of the mountains in March won't help the irrigators in southern Alberta who need to irrigate in June and July. These changes and others across the country are leading to unsustainability of our fresh water and an emerging water crisis in Canada. But I believe that we could help solve those problems by creating and mobilizing the knowledge we need to predict and respond to those problems and opportunities using flood and water supply predictions and operating these at a national scale, and then strengthening our water management to avoid disputes, adapt to climate change, reduce flood risk, preserve ecosystems, recognize the rights of Indigenous people, and grow the economy. So I'll wrap up there, and I want to recognize the artists who produced some of the artwork you see. Gennady Ivanov, who's a British artist, works as artist in residence for Global Water Futures, and has a display right now at the Russian Embassy in London. So thank you very much.
Thank you, John. That was really interesting. I'm going to ask John a couple of quick questions right now, but I invite you all to enter your questions into the chat box, and we can ask a few more after we hear from Caroline as well. So just send them either directly to me or to everyone in the chat box, and we'll make sure we try and get to some of your questions based on John's talk, and if you have any for Caroline once she's finished as well. I first met John, or got to know John quite well during the 2013 flood. Sorry, I think I said 2015 earlier. So John, how did the flooding in Calgary change your research direction?
Well, before that flood, I was not a flood hydrologist, and sometimes the floods come to you. So we had a heavily instrumented set of research basins in the mountains, and where I was living in Canmore, and we had 15 researchers in the field. And of course, we were personally impacted by the flood, much as other people. But also, we found ways to keep carrying on measurements during the flood so we could understand the mechanisms that generated that high stream flow. And so we might find ways to better predict them in the future. Also being in Canmore, looking around, we realized a massive event was coming, and also that the town of Canmore was evacuating people many hours before the provincial warning was able to come through to tell us to do that. And that was an early indicator that perhaps our forecast and prediction systems even in a wealthy, advanced province like Alberta, we're not up to these types of extreme events that were coming our way.
So certainly had an impact for Alberta and down the line in Saskatchewan and Manitoba as well with the same water basins. But what are we seeing across Canada when it comes to climate change and how it's changing both flooding, forest fires, that type of thing?
Yeah, massive changes in these. The impacts of climate change are largely manifested through the water system, through the hydrological cycle. And so you get an acceleration of the hydrological cycle, so more extreme floods and tied with more extreme droughts. The cycling back and forth is becoming sharper due to change in atmospheric dynamics. But also at the same time this is occurring, that we've increased our population in Canada. We've continued to develop in our floodplains, and so we've made ourselves more vulnerable as well in many parts of the country. We also have flood defenses, which were designed based on statistics and principles developed in the 20th century. And so they may not be always suitable for the changing extremes that we're experiencing going forward. And the drought of 2001 was also a massive one. It actually extended from 1999 to 2004, but it was $6 billion of economic damage in the prairies and 41,000 jobs lost in 1 year. And when you get a drought like that in the mountains or in the north, you think of it not as much as a drought, but as a forest fire season. And that's exactly what happened in British Columbia in recent years with record forest fires, but previously in Yukon and northern Saskatchewan and Ontario and in Quebec. It's just sort of moves across the country, but there's generally a bad fire year somewhere in Canada every year. And these are, because of the extent and intensity of these fires, often destroying the peat or continuing to burn in peat for a long time. They result in large emissions themselves of greenhouse gases. And in some cases, the ecosystem changes associated with them don't appear to be reversible. We're not always seeing forest reestablishment there. And even fires in the Yukon mean that the northern tree line is not necessarily moving northward into the tundra. It's actually retreating from the tundra as fires limit it. So we're seeing a tremendous change in our forest structure because of these fires. And then, of course, horrific events like the fires around Fort McMurray or Slave Lake earlier in this decade.
And one of the other things we talked about getting ready for this was that it's winter in a lot of places in Canada already. I think most of Western Canada anyway. And for those of us who love winter, that we're seeing less and less snow. What does this, what does this mean for snow cover and the implication of that for glaciers?
Yes, well, it is highly variable, depends where you are. In many parts of Canada, this winter came in early and came in with an unprecedented bang. One of them is the city of Saskatoon, which right now has the highest snowpack on the ground in the city it's ever recorded. And it's only November. So the winter is yet to come. So that's it's going to be very interesting in Saskatchewan this year as they cope with a snowpack that certainly exceeds anything seen in recent lifetimes. In the mountains, we're seeing dramatically lower snowpacks at lower elevations. They've dropped in half in the valley bottoms around the Kananaskis and Bull Valley, but we're still seeing steady snowpacks, sometimes even increases at the highest elevations, but we don't expect this to last. And we now experience rainfall events every month of the winter on a regular basis. So we're starting to see that shift into that rain system. And the danger there is that, the wetter winters might give you a deeper snowpack that lingers a bit longer, but then the intense rainstorms of the spring bring rain on snow events. And that's what drove part of the Calgary Flood. It drove the Ottawa River flooding a couple of years ago, New Brunswick flooding, rain on snow events. And these are very dangerous and appear to be an increasing phenomenon across the country.
For sure. We'll now turn it over to Caroline for her discussion, which will give us a little bit more on how this is affecting glaciers.
Thanks, John and Colette. I'm just going to share my screen here. So as Colette introduced me earlier, I'm a graduate student in John's group based in Canmore, and I really focus mostly on what is going on in the upper mountains, in the snow and ice dominated mountains of Western Canada. So I'm just going to zoom in a little bit more to add on to what John was discussing about the fast changes that we're seeing in these environments. And so sometimes something that we face a little bit when we study specifically the mountains is that not everyone across Canada lives with mountains in their backyards. So for a lot of people, they feel quite disconnected from what is going on in the mountains. And I just wanted to show in a few different ways how mountains are actually part of Canadian cultures in multiple ways. From on the left here, we have the initial exploration of the Canadian Rockies when we had Swiss guides that brought tourists in the mountains to them explore, or the spiral tunnels in Kicking Horse Pass, which was the link to create the railroad across the country to unify the provinces, which was an engineering feat. In the middle, we have painting from G.H. MacDonald and Lauren Harris, who were two painters of the Canadian Group of Seven, which was really the first major Canadian national art movement. And they spent quite a bit of time in the Rockies and painting the beautiful mountain landscapes. And now these paintings are in art galleries, mainly in Ontario, but really are across the country. And then finally, winter sports, which require cold, require snow, which are really one of the main ways that we can enjoy our winters, in long and cold winters in Canada, from skating or my favorite sport, skiing, where we need, at least for skiing, we definitely need some kind of mountains to be able to do it. So just wanted to show a little bit that even you might not live right next to mountains, but mountains influence different parts of Canada in different ways. But mountains are changing. So what I'm showing here is the Adabaska Glacier. It is located in Jasper National Park, and we have the first picture in 1914 and the next picture in 2016, and we can really see the drastic glacier retreat that has happened between the two. The road that currently brings tourists across the mountain range between Lake Louise and Jasper wouldn't have been able to be there in 1914 because it was covered in ice. And the Atapascar Glacier is kind of a very important one. It's a glacier that you can now take a bus and go onto the ice to actually experience firsthand what a glacier looks like. So it's kind of an important one in Canadian culture, and it's one that we've been studying quite a bit. And it shows that glacier retreat is not a new phenomenon. It's been occurring for the last century, but it's retreating in the recent decades. So this is Pedro Glacier. It is the main site of my research. As John introduced it, it is a well-studied mountain glacier. We have a lot of data, which really allows us to understand what's going on in that environment. And so what I'm showing on the left is the glacier outlines from satellite imagery. And we see that the glacier toe has really retreated in the last 20 years. And in fact, that has caused a lake to appear. So that prominent lake that we see in the toe of the glacier, that didn't exist until 2006. So in human lifespan, in different visits that you might do different years to that environment, you can see the change, drastic changes before your eyes. And even at a smaller time scale, at an annual year to year, you can see some drastic change. These two images are from the toe of Pedro Glacier, so the bottom part of the glacier, and they are from 1 year apart, so August 2019 and August 2020. And where they are red arrows, these are a collapse of the glacier toe. So we had areas on the glacier that within 1 year just disintegrated. And that is not something that happened a lot in the past. These are new features that are starting to appear more and more as we see accelerating disappearance of mountain glaciers. And these are very visually striking. It actually is making access to the glacier really difficult, and it's making our research there much more difficult now because it's hard to get on the ice to access our measurements. But we don't only have these drastic collapse and these sinkholes and these caves collapsing on the glacier. We have overall, the entire glacier is melting quite a lot. So what we're looking at now is the difference between the two pictures. So we have a LiDAR, which is a laser beam that measures the distance between our instrument and the surface. It really measures height change. And we fly it on a drone, on a little UAV, and it allows us to map the surface height of the glacier at different times. So we did that in 2019 and 2020, and we can see that we had 6 meters melt, 6 meters of melt in 1 year on that glacier toe, which is where it's red on the image. And this is a lot considering that last summer we had a very late spring and it was really cold in the beginning of summer, and then there was a lot of melt in the end of the summer. So considering that this was not even a really hot and long summer, 6 meters is a lot. And it really kind of puts in perspective how quickly that glacier is disintegrating and how fast it's changing. And that has an impact for a wide range of reason, because the glacier meltwater originating in the Canadian Rockies and Western Canada in general, not just Plato Glacier, but the entire mountain range, reaches far and wide, may it be for recreation, canoeing or fishing on the alpine lakes, or for irrigation, mainly in the Columbia Basin that drains into the United States. Some of the water from these mountains reaches cities. It's used for drinking water, and it's also used for hydropower, where the meltwater can fill the reservoirs over the summer. So even if you don't live right next to a glacier or with mountains right in your backyard, like we do here in Canmore, glaciers have an impact on everyday life across the country. But as climate change is impacting glaciers directly through change in temperature and change in precipitation pattern, like John showed, climate change also impacts glaciers in other ways. And one of the examples is the increase in forest fire activity that we see across the globe, really, which we've heard about. We've had really high forest fire activity in recent years. Well, what happens with these forest fires is that it creates big smoke plumes that can then drift over to the mountain and impact their melt. So for example, in 2018, we had really bad, really active forest fires in BC and in the United States, and that smoke drifted across a large part of the country, and it reaches one of our study sites, the Columbia Icefield, which is where the Atapascar Glacier is, which I showed in the first slide. And just to show a little bit how it looks when we have smoke at the Columbia Icefield, on the left is a sunny picture at the Columbia Icefield. The purple dots are where we have measurements to record the weather, the amount of sun, the wind, to better understand the melt. And on the right is how it looks when it's covered with smoke. And you can see this blanket of yellowish haze that really covers the entire toe of the glacier. And what happens is that smoke deposits soot on the surface of the glacier, which darkens the surface and increases melt. So some of our simulations and the work we've been doing in that environment show that we have an increase in up to 10% of the melt due to the fact that the surface gets darker. So we often picture a glacier as this bright blue, pristine environment, but in fact, the glaciers are getting darker and darker. And the darkness, the soot that's stuck on the ice surface, it doesn't go away, it doesn't wash out after a year. It stays there and it crusts instead of the surface. So it can have multiple years of impact on the melt. And then if we kind of look at future change in the Canadian Rockies, different studies predict that up to 85% of Western Canada's glacier are expected to disappear by 2100. So that means we have a catchment currently at Pedro, which is this little cartoon that is about 50% glacierized, snow and ice dominated, it's cold, beautiful big glacier. By 2100, that ice will be mostly gone and there might be just a little bit of glacier left at the top of the mountain. And that impacts the hydrology. So here we're looking at how much water would be in the catchment at Plato Glacier between October, so throughout the winter and then the spring melt. In black is our current between 2000 and 2015 hydrology. And in red is what our simulations and our hydrological model predict for the end of the century. And we see that we have quite a difference in stream flow in that environment. We have a 50% decrease in the summer. We have a 90% increase in the spring and June. So we have a huge shift in timing and in flow at different times of the year. And we have winter flow as well. So really this retreat of glacier caused by climate change will impact the hydrology in these high mountains. So overall, glacier meltwater reaches far and wide. You don't need to have a glacier in your backyard to realize that mountains are important. The water is contributing to irrigation, hydropower, and recreation. Mountains are impacted by climate change in more than one way. Nothing works in isolation. The different systems are connected. So for example, forest fire soot can deposit on the ice and increase melt. And this ongoing glacier retreat will shift the timing and the volume of water resources, increasing spring flow, and strongly decreasing summer flow.
Thanks, Caroline. Fascinating stuff. I remember as a kid walking up to the toe of the Atapascar Glacier and doing it again about 3 years ago. And despite being a lot taller now, it being a lot farther walk these days. And I think that's evidenced by the markers that they have there as well. It's quite stark to walk up to it. Tell us a little bit more about what the loss of glaciers means for recreational opportunities and culture, tourism, that sort of stuff.
I think so. Here in the mountains, skiing is a huge component of everyday life. People go to tour in the mountains, and with the glacier retreat, some of these areas that we used to access are not accessible anymore. So it's becoming more and more difficult to get into the mountains because these glaciers are retreating. And with climate change, the snow supply is changing. So potentially powder days will become harder and harder to get. And so it's impacting our everyday life, I would say, quite a lot. And even just in terms of scenery, some of my first memories being in the Canadian Rockies was driving and staring out the window and looking at all the glaciers in the top of the mountains. And that is potentially not going to be there anymore in a few decades. So I think it's going to be changing the experience that we have in this landscape
yeah, there's
significantly.
Something special about snow-capped mountains, isn't there?
Yeah.
Yeah, we can now open it up to questions. We have about 15 minutes left. So I don't see anyone typing in questions, but if anyone, we've got quite a small group, so we can either ask them directly, or if you have a question that you'd like to ask, just unmute yourself if you can. I don't know if that's possible, and feel free to ask it. Does anybody out there have questions? If not, I have a few more, so just let me know. No one? Everyone's shy today. Okay, well, I have a couple more questions that I'd love to ask. One of the things we've seen dominate, obviously, the news coverage this year and our lives this year has been COVID. COVID-19 has been a big topic, obviously, not only in our lives, but at this conference as well. How has COVID-19 affected your research and your ability to do that research, both for John and Caroline?
Caroline, I'll start. For my own research, I mean, the initial thing was that at universities, our campuses shut down and we were working from home. And initially our field work was shut down. So that caused us to miss the peak snowpack buildup in the Rockies this spring. Eventually we found ways to permit some field work going out, but we had to be very, very careful with it. And so driving out in separate vehicles, if you're not handling the same equipment, making sure we're spaced apart, we're generally outdoors for field work, so that part's all right. But you have to prepare in the lab instruments and download programs on computers and other things in a lab, and so you have to proceed very carefully in the lab and generally by yourself. Occasionally, normally going to Pedro, there's a hut up there built by Environment Canada's predecessors in the 1960s. And normally we would overnight in that hut, but we can't together in a cramped location now. So that means we can't get in and out of there in one day, which means a helicopter, which is, it's expensive. It's about $6,000 to get one set up to go in there. And, but then you're in a confined helicopter with other people who could be contaminated. So I had a trip scheduled up there for tomorrow, which I've had to cancel just because of the risk of COVID. But but I think the impact on professors such as myself isn't so bad. It's on graduate students and young scientists that a master's student has one field season to collect their data to move forward outdoors, and many of them have lost their field sessions. A PhD student might have a chance for two, but they need both of them to work. And so this can be devastating. And also the loss of contact with students and supervisors and the whole academic community. Again, it's bad enough for professors, but we know lots of people. But when you're starting out, I think it must just be awful. And Caroline, you can probably bring forward much more. The final thing I'll say is those with young families or dependent family members that they're caring for, simply had to pull back their activities from field science and field research under this condition of COVID, and that brings an equity issue into the whole thing.
Yeah, I was supposed to, I had a plan to go monitor the Plato Glacier fairly often this summer because of this sinkhole that opened in the toe. That's a very interesting feature. I wanted to go and monitor how it was expanding and how it was growing, but with COVID hitting, it just didn't happen because I would have had to start early in the summer when we were shut down. And it would have required quite a lot of visits with the field techs, and it just didn't happen. So that's one project that really was time sensitive. If now it's too late, it would have had to happen this summer. So there's definitely a gap in the data collection that we do that really prevents us from getting a complete picture of what's going on. So I was really hoping to do that. But at the same time, I'm lucky enough that a lot of my work is via computer simulations, and it's a lot of data analysis that I've already collected. So I was able to keep doing my work, as I know it hasn't been so easy for a lot of other people. I just saw a question about a Mountain Legacy project. So those were the images that I showed in my presentation. It's a really interesting project. It's impressive to go look at the images online. We don't work with them. I use their images a lot to put my work in context, but they do longer time spans. So it's about a century in between the old pictures and the new one. And I mostly look at future change and try to understand how the current conditions are going to affect the future. So I don't work with them, but I'm so happy that that project exists to provide these visual striking images.
Yeah, it's a great project for sure. There's also another question. Do you also try to predict the impact of warming on animals and insects? So wild animals and insects. Do you guys do any of that work, or is it strictly focused to water?
Our research is on water and the water environment, but the snowpack work we do ties into the snow ecosystem quite a bit. And a few years ago, I was involved we published a book on snow ecology. So there are profound impacts through the snow system on animals and insects. There's a whole ecosystem and food web in the snowpack, in the nibble system. And of course, it depends on the properties of that snow, the depth of the snow, its density, and particularly the temperature and liquid water content and nutrient content of the snowpack. The snow provides a relatively warm shelter for many organisms. And so if you have a year without snow or with very shallow snow, then these organisms are exposed, whether they're voles under the snowpack or snow spiders or collembola that would come out in the spring and look like pepper over the snow. But also then you have larger animals that graze over the winter, and rain on snow is a big problem for them because it often leaves ice layers in the snowpack, and they can't paw through that. So, and this has resulted in extirpation of the prairie caribou from some of the Arctic islands in recent history, and other localized events that have caused mass starvation of grazing animals over snow. And we know even for agriculture, the big snow years also are problematic, and the end of the open range in the Canadian prairies in the 1880s was associated with the very harsh winters that the cattle simply couldn't feed on the natural grasses in southern Alberta and Saskatchewan as they could in other years.
Interesting. I don't see any more questions at this point, but I can ask another one. What are some of the water-related projects that that are happening in your area related to COVID? I think we've seen some with evaluating sewage water, I believe.
Yes. Global Water Futures funds 51 projects at 18 universities across Canada, and some are associated with looking at environmental DNA organisms and other toxicological aspects of organisms, and researchers primarily at Saskatchewan and Waterloo universities. And they've been developing techniques to look at sewage effluent and as a predictor of COVID infections, because not everybody can get tested or even knows they're ill, but we all emit virus when we're infected, and that can be the virus residues and particles can be detected in sewage water. And so my colleagues, John Giese and Marcus Brinkman and others at the University of Saskatchewan have been doing this in Saskatoon and very correctly predicted an exponential increase in caseloads in Saskatoon, which sadly has come true in the last week. And the results are still showing a very unpleasant next few weeks for Saskatoon as an example. And others across the country have been developing and deploying this information. And so it's sort of putting water science to work for society right away. And it's a massive shift for the scientists to get this sort of technique developed in short order, but certainly very necessary.
Yeah, it's been interesting to watch how quickly some research is coming out these days. Obviously, COVID and climate change are maybe moving at different paces, but both have huge implications for science and scientists. The Public Health Agency of Canada has obviously had a major role in dealing with COVID-19. How might a Canada Water Agency deal or help with future climate change issues?
We'd hope that a Canada Water Agency would have a chief scientist of the quality of Dr. Tam in the Public Health Agency of Canada, someone who could bring information forward to the provinces and water managers and to the public in times of environmental crisis, which we're almost certainly will be seeing more of, whether they're major floods or droughts or fires. And what's critical is to get information out in those events so that municipalities, industries, the regular population can make decisions to keep themselves safe, to inform emergency management organizations along with provincial agencies that provide this function. And because these events are not limited to one province or one municipality anymore, what we call the Calgary Flood started in British Columbia and Alberta, and then the next evacuations were Cumberland House at the eastern edge of Saskatchewan. So it actually involved 4 provinces because the water flowed to Manitoba. And so these are national issues. The Ottawa River flood obviously involved both Quebec and Ontario through there. And so we have to bring people together for this. And I'm hoping in Canada Water Agency, through its information and the convening power that it would have, can provide national leadership, not just federal government leadership on this issue.
For sure. We have like about 3 minutes left, but I see that there's one more question from our audience members. So as an archivist, Tom Nesmith says it strikes him how the photos and other data that you've amassed may be the only thing left to tell future generations what a glacier was like, much like the photos of demolished buildings. Does that cross your mind at all? This archiving your material is crucial for that reason too.
Yes. I used to work at Environment Canada. We had a Canadian Glacier Inventory Center, which had photographs, the data, the field notes, everything from the massive amounts of glacier studies that Canada conducted from the 1940s through to the 1990s. Unfortunately, Environment Canada moved out of glaciology. That Glacier Inventory Center we can no longer find it. But one of the scientists who developed it, Simon Omany, kept copies of the collection as his personal collection. Simon passed away just last month, very sadly, and profoundly donated his collection to the University of Saskatchewan. We have it in the Center for Hydrology now. There's 28 boxes of data and photographs, and we're going to find a way to preserve this for future generations. And we're working with Environment Canada now to find where they have archived somewhere the collection of the original Canadian Glacier Inventory. This is absolutely crucial that we do this and take that time right now, because we're losing the subject that we're studying, and we have to maintain the detailed records so people understand what an ice age looked like in Canada in the highest mountains, and because they won't be able to go and see it and touch it as we can now.
Wonderful stuff. I think we're at our time. Does anybody else want to make a comment? I put it out there for one last comment if anyone has it. Otherwise, I think that's it. So John, do you want to offer a closing comment? Okay, Caroline.
Caroline, why don't you say something?
Well, first, I guess, thank you, John, for inviting me here and talking. And thank you for everyone that came to take the time out of your day in an environment that is very busy, especially now we're all online all the time. So I think we all appreciate greatly that you took the time to come and hear what we have to say about the importance of water resources in this climate crisis.
Thank you. And I see Professor Sylvie Romanowski on the call, and just want to recognize her and again, the wonderful contributions of her father through this award, and in respect of his own contributions to measurement. And we've shown lots of very careful measurements here. So we're trying to carry on that metrology tradition as well. Thank you.
Thank you very much, John. Appreciate that.
Thank you for being here, everyone, and have a great day.